I woke for the third time that night and crawled from under the beaver pelts to tend the fire. The Longhouse was cold, not brutally cold, but cold enough that my breath condensed in visible clouds, cold enough that my fingers stiffened as I reached for wood from the stack beside the fire pit. Outside it was probably 15 degrees, maybe colder. Inside, maybe 40. The fire had burned down to coals again, losing its heat to the darkness above, and I was tired of waking every 2 hours to rebuild it. This was my first winter night in the Haudenosaunee Longhouse, guest of a Mohawk family in the valley west of the Hudson River. December 1791. I'd come to observe and document their building practices, their methods of surviving winter, in these structures that seemed, from the outside, too thin-walled and too large to heat effectively. The Longhouse was perhaps 80 feet long, 20 feet wide, with a barrel-vaulted roof covered in elm bark. 2 fire pits ran down the center line, spaced maybe 30 feet apart. Each fire pit served 2 families, one on each side of the central corridor. I'd built the fire the way I knew, kindling at the bottom, progressively larger pieces stacked above, the whole structure designed to burn upward with flames reaching high. The fire had burned well for the first hour, throwing heat in all directions, but mostly up toward the smoke holes in the roof. By the second hour, it had consumed the kindling and was working through the larger pieces. By the third hour, it was coals. I'd added more wood, rebuilt the structure, and the cycle repeated. Now, at what I guessed was 3 in the morning, I was rebuilding again. I was burning through wood at a rate that seemed unsustainable, an armload every 2 hours. The family I was staying with hadn't said anything, but I could sense their quiet amusement. They'd built their fire once, at sundown, and hadn't touched it since. Their fire pit still glowed with heat, still radiated warmth, though I couldn't see flames. Mine required constant attention. When dawn finally came, gray and cold, I gave up on sleep and sat examining the fire pit itself. I'd assumed all fire pits were roughly the same, a depression or raised area where you contained fire to prevent it from spreading. But looking at this pit in morning light, I saw it was built differently than I'd expected. It wasn't raised above the floor. It was recessed into it, dug down, with the bottom of the pit sitting well below the packed earth floor of the Longhouse. I knelt beside it, running my hand along the edge. The pit was lined with stones, river cobbles, smooth and rounded, each about the size of my fist. The stones extended down into the pit, forming walls maybe 18 inches deep. At the bottom, more stones laid flat, creating a floor. The pit was rectangular, roughly 3 feet by 4 feet, perfectly sized for the long logs that the Mohawk used. Hardwood, oak, and maple, cut to length and split into manageable pieces. What struck me was the depth. Why dig down? Why not build the fire pit up, creating a raised hearth that would radiate heat at waist height, where it would warm people more effectively? Digging down seemed counterintuitive, seemed like you'd be putting the fire in a hole where heat would be trapped rather than radiated into the living space. The elder of the family, a man named Tekarihoken, had been watching me examine the pit. He smiled, said something in Mohawk that I didn't understand, and gestured for me to wait. He left the Longhouse and returned with several large logs, oak from the look of them, each maybe 8 inches in diameter and 3 feet long. He also brought an armload of smaller wood, progressively smaller pieces, from branch-thick down to kindling-sized. He began to build a fire, but not the way I had built mine. He started with the largest logs, laying them flat at the bottom of the pit. 3 logs, side by side, filling the pit's bottom. Then a layer of slightly smaller logs, laid crosswise. Then another layer, smaller still. He continued this pattern, each layer smaller than the one below, until he reached the top of the pit, where he placed kindling and small sticks. The entire structure was inverted from what I knew, large fuel at the bottom, small fuel at the top. Then he lit it. He used a coal from the previous night's fire, still glowing in the ash, and placed it on the kindling at the top. The kindling caught, flamed, and began burning downward through the layers. The fire wasn't reaching up, it was working its way down, consuming the smaller fuel first, then progressively larger pieces as it descended into the pit. I watched for an hour, fascinated. The fire burned hot at the top initially, consuming the kindling and small wood rapidly. But as it burned down through the layers, the combustion slowed, became more controlled. The larger logs at the bottom didn't flare and flame. They burned steadily, with deep red. Coals forming, heat radiating from the entire mass of burning wood rather than just from flames. By mid-morning, the fire had burned down to the bottom layer of large logs. Those logs were now coals, glowing red, sitting on the stone floor of the pit. But the pit itself was radiating heat, intense heat, more than I'd felt from my overnight fires. I held my hand near the pit's edge and felt warmth pouring out, not just from the coals, but from the stones themselves, from the earth around the pit. Tekari Hokan said something else in Mohawk, gestured to my fire pit, the one I'd been tending all night, and then to his. The message was clear. I'd been doing it wrong. The fire wasn't supposed to burn up, it was supposed to burn down. The pit wasn't just a container, it was part of the heating system, and I'd just witnessed the first step in understanding why this design worked. I spent the second day studying the fire pit's construction, while the family went about their daily routines. Tekari Hokan had given me permission to examine it closely, even to dig around its edges if I did so carefully. I wanted to understand not just what I'd seen, the inverted fire burning downward, but why the pit was built this way, what purpose the depth and stone lining served. The pit dimensions were precise. I measured with hand spans and a piece of cord, 42 inches long, 36 inches wide at the top, tapering slightly toward the bottom, maybe 34 inches by 30 inches at the base. The depth was consistent, 18 inches from the floor surface to the stone floor at the pit's bottom. 18 inches of excavation, lined completely with river stones set in clay mortar. The stones themselves were carefully selected. Not just any rocks, these were dense, fine-grained river cobbles, each roughly the same size, each positioned to maximize contact with its neighbors. The selection mattered, I realized. Porous stones like sandstone would crack and spall when heated. Shale would split along its layers. But these dense river stones, likely granite or basalt, smoothed by water, could withstand repeated heating and cooling without failing. I examined the mortar between the stones. It wasn't just clay, it was clay mixed with sand and something organic, finely ground plant fiber, maybe cattail down. The organic material would burn away when first heated, creating tiny voids in the mortar, but those voids would actually help. They'd allow the mortar to expand slightly during heating without cracking. The builders had understood that a rigid mortar would fail, a slightly flexible one would last. What intrigued me most was what lay beneath the stone floor. I carefully removed one stone from the pit's floor. Tekari Hokan watched but didn't object, and found compacted earth below, then a layer of sand, then more earth. The sand layer was perhaps 3 inches thick, perfectly level. This wasn't structural. The sand was too loose to support weight. This was thermal. Sand has different heat capacity and conductivity than clay or soil. The sand layer would absorb and store heat differently than the surrounding earth. I replaced the stone and examined the pit walls. The stones extended the full 18 inches of depth, creating a complete liner from floor to rim. But beyond the stones, behind them, was packed earth. Not loose backfill, but deliberately compacted soil, tamped solid. I pressed my hand against the earth outside the pit, then against a stone inside the pit. The stone was warm from yesterday's fire, still radiating heat. The earth outside was cool but not cold. It had absorbed warmth through the stone layer and was holding it. The pit's edges, where it met the Longhouse floor, were sealed with more clay mortar, creating a smooth transition. There was no gap where cold air from beneath the floor could infiltrate, no opening where heat could escape laterally. The pit was thermally sealed, connected to the earth below, but isolated from the airspace of the longhouse around it. I sketched the cross-section in my journal, floor level, then 18 inches of stone-lined pit, then the sand layer, then earth extending downward indefinitely. The pit wasn't just dug into the floor, it was excavated deep enough to tap into the thermal mass of the earth itself, to connect the fire to the stable temperature zone below the frost line. That afternoon I examined the second fire pit 30 feet down the longhouse to see if its construction matched the first. It did exactly. Same dimensions, same stone lining, same careful mortar work. The consistency told me this wasn't a casual design. This was a refined standard, a template that builders followed because they knew it worked. I thought about the excavation effort. Digging 18 inches into frozen or hard ground with stone tools would be substantial work, hours, maybe days per pit. Why accept that effort? Why not build a raised hearth with stacked stones, which would require no excavation at all? The only reason to dig down was if depth provided some advantage that height didn't, some benefit that justified the extra labor. The answer, I suspected, was thermal coupling. A raised hearth sits on top of the floor, radiates heat into the air, loses heat in all directions. A recessed hearth connects to the earth, can store heat in the ground itself, can tap into the earth's mass as a thermal reservoir. The builders had chosen to work with the earth rather than build above it, to make the ground itself part of the heating system. By evening, I'd measured everything measurable: depth, width, stone size, mortar thickness. I had detailed sketches, cross-sections, notes on materials, but I still didn't fully understand how the system worked, how burning a fire downward into this pit would heat the entire longhouse all night. That understanding would come through observation, through watching the fire through a complete cycle from lighting to extinction. On the third day, Takari Hoken allowed me to build the fire myself, following the inverted method he'd demonstrated. He watched as I selected logs, 4 large oak pieces, each about 8 inches in diameter, for the bottom layer. I laid them flat in the pit, parallel to each other, filling the stone floor. The wood rested directly on the stones, with maybe an inch of space between logs for air circulation. For the second layer, I chose slightly smaller pieces, maybe 6 inches in diameter, and laid them crosswise to the first layer. This created a grid pattern with air gaps at every intersection where the wood crossed. The third layer, smaller still, laid parallel to the first. Fourth layer, crosswise again. I continued until I reached the top of the pit, where I placed kindling and dry bark strips for ignition. The structure looked precarious, top-heavy, like it might collapse as it burned. But Takari Hoken nodded approval, so I continued. I used a coal from the morning fire, placed it on the kindling at the top, and blew gently. The kindling caught, flames spread, and the fire began burning downward through the layers I'd built. The burn pattern was unlike anything I'd seen. The top layer consumed quickly. The kindling and small wood flared, burned hot, and converted to coals within 20 minutes. But instead of collapsing into chaos, the coal settled onto the second layer, began heating it, preparing it for combustion. The fire was self-feeding, each layer igniting the one below, the heat working steadily downward. I knelt beside the pit, watching the progression. The second layer began to burn, not with high flames, but with steady, glowing combustion. The wood gasified, released its volatile compounds, and those compounds burned as they escaped. The coals from the first layer provided the heat necessary to sustain this process, and the geometry of the stacked wood ensured adequate airflow without creating a draft that would burn everything too quickly. After an hour, the fire had reached the third layer, the 6-inch diameter logs. These were burning slowly, thoroughly, converting to coals rather than flaming. The heat was intense but contained, radiating from the entire surface of the burning wood rather than from a concentrated flame. I could hold my hand a foot above the pit and feel steady warmth, not the searing blast of heat from a conventional fire. What struck me was the smoke, or rather, the lack of excessive smoke. The inverted fire produced surprisingly little smoke compared to my fires from the first night. The wood wasn't smoldering, it was burning completely, converting almost entirely to heat and ash. The controlled combustion, the adequate but not excessive airflow, the high temperature in the pit, all of this created conditions for clean, efficient burning. By mid-afternoon, the fire had reached the bottom layer, the large oak logs lying on the stone floor. These were burning with deep, glowing coals, no visible flames, just radiating heat. I measured the temperature near the pit's edge, too hot to hold my hand close for more than a few seconds. The stones lining the pit were absorbing this heat, conducting it into the earth behind them, storing energy in the thermal mass of the ground itself. Tekarihokin added more large logs on top of the burning coals, 4 more oak pieces laid flat. These would burn down through the afternoon and evening, maintaining the deep coal bed, continuing to heat the stone and earth. This was the rhythm of the inverted fire. Build large fuel at the bottom in the morning, let it burn down through the day. Add more large fuel in the evening, let it burn through the night. I stayed by the pit all afternoon watching, measuring, trying to understand the physics. Heat was radiating upward from the coals, of course, that was basic thermodynamics, but heat was also radiating laterally from the pit walls, warming the floor around the pit, and heat was conducting downward through the stone floor into the sand layer and earth beneath. The fire was feeding heat in all directions, not just up. As evening approached, I realized the pit was functioning as a heat distributor, not just a fire container. The burning coals provided input energy. The stone walls and floor distributed that energy, some upward to the air, some laterally to the surrounding floor, some downward to the earth. The distribution was more even, more controlled than a conventional fire, where most heat escapes upward and is lost through the smoke holes. That night I watched Tekarihokin prepare the fire for sleeping. He didn't add small wood. He added large logs, the largest he had, perhaps 10 inches in diameter. 3 logs laid flat on the existing coals. Then he used a wooden paddle to adjust the coals, spreading them slightly, ensuring even contact with the new logs. Finally, he sprinkled a thin layer of ash over the top, partially covering the coals, slowing their burn rate. The fire settled into a slow, steady state. No flames, just glowing coals, mostly hidden under ash, burning imperceptibly slowly. The heat output dropped. The intense radiation was gone, but the pit continued to release warmth. I could feel it with my hand held over the pit, a gentle but persistent flow of heated air. I slept well that night, warm under the beaver pelts, and I didn't wake to tend the fire. Neither did Tekarihokin. The fire managed itself, burning at exactly the rate necessary to maintain heat through the night, sustained by the thermal mass of the heated stones and earth. The 4th morning, I woke to a longhouse that was comfortably warm. Not hot, but noticeably warmer than the outside air. I checked my thermometer. Outside, 18 degrees Fahrenheit. Inside, near the fire pit, 56 degrees. At the far end of the longhouse, away from the fire, 48 degrees. The temperature distribution was remarkably even considering the longhouse's size. The fire had burned down overnight to a bed of coals, still glowing faintly under their covering of ash. Tekarihokin uncovered them, added kindling and small wood to rebuild flames, then added larger logs once the fire was established. The morning fire cycle had begun, but I was more interested in what had happened overnight, in how the fire had heated the space for 8 hours with almost no new fuel added. I asked permission to measure the stones in the pit, to understand how much heat they'd stored. Tekarihokin agreed, but warned me with gestures that the stones would be hot. I used a long stick to probe the ash and expose a section of the stone floor. Even after a night of slow burning, the stones were hot. Too hot to touch directly, hot enough that I could feel radiant heat from them when I held my hand 6 inches above. I wanted to measure temperature at depth to understand how far into the earth the heat had penetrated. I found a metal rod, a ramrod for a musket, borrowed from the family supplies, and pushed it into the sand layer beneath the pit. This required removing several floor stones first, digging through the sand, and inserting the rod to a depth of about 12 inches below the pit floor. I left the rod in place for several minutes, then withdrew it and touched it carefully. The rod was warm along its entire length, not surface hot like the stones, but noticeably warm, indicating that heat had conducted through the sand layer and into the earth below. I calculated roughly. If the stones were at, say, 400 degrees Fahrenheit at the surface and the earth 12 inches below was at 100 degrees, heat was conducting downward through all the material in between. The sand layer, which I'd measured at 3 inches thick, was acting as a thermal buffer, slowing the heat transfer somewhat, but allowing it to continue. Below the sand, the earth itself was absorbing heat, storing it in its mass. How much heat? I estimated the volume of earth that could be significantly heated, maybe a hemisphere extending 2 feet down and 2 feet out in all directions from the pit center. That's roughly 33 cubic feet of earth, weighing perhaps 3,500 pounds at 100 pounds per cubic foot. If that earth was heated from, say, 40 degrees to 80 degrees, a 40-degree rise, it would store roughly 28,000 BTUs of energy. That's equivalent to burning about 4 pounds of wood, except this energy was stored, not immediately released. The stones themselves stored additional energy. I estimated perhaps 800 pounds of stone in the pit lining and floor, if heated. From 40 degrees to 400 degrees, that's 360 degrees of temperature rise. Stone has a specific heat capacity of about 0.2 British thermal units per pound per degree Fahrenheit. So 800 pounds times 360 degrees times 0.2 equals 57,600 British thermal units stored in the stone alone. Combined, the stone and earth beneath the pit were storing roughly 85,000 BTUs, the equivalent of 12 pounds of wood. This was energy that would release slowly overnight, maintaining warmth long after the fire died down to minimal coals. This was why the inverted fire worked. It charged a thermal battery, and that battery discharged through the night, keeping the Longhouse warm. I shared my calculations with Tekari Hoken through sketches and gestures. He couldn't read numbers, but he understood the concept. The ground under the fire got hot, stayed hot, gave heat back, slowly. He nodded, smiled, and pointed down at the pit, then at the Longhouse floor around us. The message was clear. The earth itself was the heater, not just the fire. That afternoon, I mapped the floor temperature around the pit. At the pit's edge, very warm, almost too hot to touch with a bare hand. 1 foot from the edge, warm, comfortable to touch. 2 feet away, noticeably warm, warmer than the ambient air. 3 feet away, slightly warm, above the floor temperature at the far end of the Longhouse. The heat was spreading radially from the pit, conducted through the packed earth floor, creating a warm zone that extended several feet in all directions. This radial heating explained why the inverted fire could heat such a large space efficiently. The heat didn't just rise, it spread horizontally first, warming the floor, which then warmed the air above it through convection and radiation. The entire floor became a gentle heater, distributing warmth more evenly than a conventional fire ever could. By evening, I understood that calling this a fire pit was misleading. It was an earth heater, a thermal mass charging system, a heat storage and distribution device that happened to use wood combustion as its energy source. The fire was temporary. The heated earth was persistent. The builders had inverted not just the fire, but the entire concept of heating. Instead of generating heat continuously and losing most of it, they generated heat periodically and stored it for gradual release. On the fifth day, I focused on understanding the airflow dynamics that made the inverted fire burn so differently from conventional fires. I needed to observe how air moved through the stacked wood, how oxygen reached the combustion zone, and why the burn rate was so much slower and more controlled than what I'd achieved with my first night's fires. I built another inverted fire, this time paying close attention to the air gaps I created between layers. The bottom layer of large logs had perhaps an inch of space between each log, enough for air to circulate beneath and between them, but not so much that the logs would collapse inward as they burned. Each subsequent layer, being cross-laid, created its own set of air passages running perpendicular to the layer below. As the fire burned downward from the top, I watched smoke behavior. The smoke rose from the burning layer but didn't billow. It drifted upward in lazy streams, indicating that the combustion wasn't consuming oxygen. Rapidly wasn't creating the strong draft that pulls air through a conventional fire. The fire was burning in a slightly oxygen-limited environment, not starved but not flooded either. I experimented by adjusting the wood placement in a second, smaller test fire I built in a clay-lined pit outside the Longhouse. First attempt, I spaced the bottom logs too far apart, maybe 3 inches between them. The fire burned too quickly, consuming the wood rapidly, generating high flames, but converting less of the wood to long-lasting coals. The excessive airflow created a draft, accelerating combustion beyond the optimal rate. Second attempt, I packed the logs too tightly, leaving minimal gaps. The fire struggled to burn downward, smoldered, produced excessive smoke. Without adequate airflow, the wood couldn't reach the temperature necessary for clean combustion. The smoke was white and thick, uncombusted volatiles escaping without burning. Third attempt, I replicated the spacing Takari Hoken had, used roughly 1 inch between logs. The fire burned steadily, cleanly, producing minimal smoke and converting the wood efficiently to coals. This spacing allowed enough oxygen to sustain combustion without creating a draft that would waste fuel. The air movement pattern became clear. Air entered the pit from the sides, drawn inward and downward by the slight negative pressure created by hot gases rising from the combustion zone. This air moved through the gaps between logs, was preheated by contact with hot wood, and reached the burning layer already warm. The preheating was important. Cold air arriving at the combustion zone would cool the fire, reduce efficiency. Warm air sustained combustion temperature while providing necessary oxygen. I traced the smoke path. Hot combustion gases rose from the burning layer, passed through the layers above, which were either already consumed or being preheated, and exited through the smoke hole in the Longhouse roof. The rising gases preheated, the wood above drying it, beginning the gasification process before flames ever reached it. This preheating reduced the energy required to burn each layer, making the overall process more efficient. The pit geometry contributed to airflow control. The 18-inch depth created a chimney effect, but a mild one, not the roaring draft of a tall chimney, just enough draw to sustain combustion. The stone walls prevented lateral air infiltration. All air had to enter from the top, through the wood layers, forcing it through the controlled pathway the builders had created. By afternoon, I understood that the inverted fire was self-regulating. If combustion accelerated, consuming oxygen more rapidly, the reduced oxygen availability would slow the burn. If combustion slowed too much, oxygen would accumulate, accelerating the burn. The system found its own equilibrium, burning at a rate determined by the wood spacing and pit geometry, requiring no human intervention to maintain. That evening, I watched Takari Hoken prepare the night fire again. He placed the large logs carefully, ensuring consistent spacing, checking the gaps with his hand. This wasn't casual work. This was precision, born from experience, from understanding that small changes in spacing would affect burn rate and efficiency. He knew through years of fire tending exactly how to build a fire that would burn through the night at the right rate, slow enough to last, hot enough to heat the stones and earth thoroughly. The airflow mystery resolved into understanding. The inverted fire worked because it controlled oxygen access, creating conditions for slow, complete combustion. The burn rate matched the Longhouse's heat loss rate, generating just enough energy to maintain comfort without waste. This wasn't a fire you fought to control. This was a fire that controlled itself, operating within the parameters the builders had designed into the system. The sixth day brought a question I'd been avoiding. Why did the inverted fire heat the Longhouse more evenly than my conventional fires? I'd assumed it was simply that the fire burned longer, but that didn't fully explain the temperature distribution I'd measured. I needed to understand how heat moved from the pit into the living space. I started with radiant heat. All hot objects emit infrared radiation, heat you can feel without touching. A conventional fire radiates heat in all directions, but most effectively upward and outward from the flames. The inverted fire, once it burned down to coals in the pit, radiated differently. The coals sat in the pit, glowing red, radiating primarily upward, but the heated stone walls and floor radiated in all directions, up, out, down. I positioned myself at different locations around the pit and held my hand at various heights, feeling for heat. At floor level, 1 foot from the pit, strong, radiant warmth. At waist height, 1 foot from the pit, moderate warmth. At floor level, 3 feet from the pit, gentle warmth. At waist height, 3 feet from the pit, barely perceptible warmth. The pattern was clear. Radiant heat from the pit was strongest near floor level, dissipating with distance. This distribution was opposite to a conventional fire, which radiates most strongly at flame height, typically 2 to 3 feet above the floor. The conventional fire heats the upper portion of a room, while the floor stays relatively cold. The inverted fire heated the floor, and the floor then warmed the air above it through convection. I sketched the heat pathways. Coals in pit radiate to stone walls and floor. Stones absorb and re-radiate heat. Floor around pit heats through conduction from pit and radiation from stone. Warm floor heats, air by convection. Warm air rises slowly, mixing with cooler air. Entire volume gradually warms. The pathway was longer, more complex, but more even. Heat didn't spike in one location and drop elsewhere. It distributed gradually throughout the space. The stone lining was critical to this distribution. Stone has high thermal mass, but also decent thermal conductivity. It absorbs heat readily and also releases it readily. The stones absorbed heat from the fire, stored some of it, and re-radiated the rest. This re-radiation continued for hours after the fire died down, long after a conventional fire would have gone cold. I measured the stone temperature at different times through the day. Mid-morning, after the morning fire had burned for 2 hours, 250 degrees Fahrenheit at the surface. Early afternoon, with the fire reduced to coals, 180 degrees. Evening, before adding night logs, 140 degrees. The stones were cooling, but slowly, releasing their stored heat gradually rather than all at once. The floor itself participated in heat distribution. The packed earth floor conducted heat laterally from the pit, warming an area several feet in radius around the fire. I measured floor temperature at various distances. At pit edge, too hot to touch. 1 foot away, warm but touchable. 2 feet away, noticeably warm. 3 feet away, slightly warm. 4 feet away, near ambient. The temperature gradient was gentle, creating a warm zone that extended well beyond the pit itself. The Longhouse's low profile contributed to efficient heating. The ceiling was only about 12 feet high at the peak, meaning the volume of air to heat was relatively small compared to the floor area. The warm floor heated this volume more effectively than a point source fire would. Heat stratification still occurred, warmest near the ceiling, coolest near the floor, but the difference was smaller, perhaps 10 degrees rather than 30. That afternoon I sat at various locations in the Longhouse, experiencing the heat distribution personally. Near the pit, almost too warm, slightly uncomfortable. 10 feet from the pit, comfortable, warm enough to sit in light clothing. 20 feet from the pit, cool, but not cold, comfortable with moderate clothing. 30 feet from the pit near the far end, noticeably cooler but still above freezing, still tolerable. One fire was heating 80 feet of Longhouse, maintaining livable temperatures throughout, despite the length. The second fire pit, 30 feet down the Longhouse, extended the warm zone. Between the two pits, there was an overlap where heat from both contributed to comfort. The builders had spaced the pits to create continuous warmth along the entire length, ensuring no cold zones where families would be uncomfortable. By evening, I understood that the inverted fire's advantage wasn't just in fuel efficiency or burn duration, it was in heat distribution. By heating the floor rather than the air directly, by storing heat in mass rather than releasing it to space, by radiating at floor level rather than ceiling level, the inverted fire created comfort more effectively than conventional fires. The distribution was the key to the system's success. The seventh evening, Tekarihokin invited me to prepare the night fire under his supervision. He would correct me if I made errors, teach me the protocol that allowed the fire to burn unattended through the night without consuming excessive fuel or dying out completely. This was the practical knowledge that made the system work, not just how to build the fire, but how to manage it through the sleep cycle. The evening fire began with assessing the coal bed. Tekarihokin used a wooden paddle to gently move ash aside, exposing the coals beneath. The coals should be deep, at least 6 inches of glowing embers covering the entire pit floor. If the coals were shallow or patchy, the night fire wouldn't sustain properly. He nodded approval. The afternoon fire had produced an adequate coal bed. Next, he selected logs for the night. The largest available, perhaps 12 inches in diameter, oak or hickory, dense hardwoods that would burn slowly. He chose 3 logs, each cut to the length of the pit. These weren't random selections. He rejected several before finding 3 that satisfied him. He was looking for wood that was dense, dry but not too dry, straight-grained without knots. Each characteristic affected burn rate and heat output. He laid the first log directly on the coals, parallel to the long axis of the pit. The logs settled into the coals, which glowed brighter where compressed. The coal bed was supporting the log's weight, while providing heat to begin gasification. The second log went beside the first, touching along their length, no gap between them. The third log went on top, in the gap between the first 2, creating a stable stack. This configuration was specific: 3 logs, not 2 or 4. 2 logs would have gaps that allowed too much air circulation, burning too quickly. 4 logs would have insufficient air circulation, smoldering rather than burning. 3 logs, properly positioned, created the optimal balance: adequate air access, stable structure, controlled burn rate. After positioning the logs, Tekarihokin used the paddle to carefully spread coals around the base of the log stack, ensuring heat contact on all sides. Then he sprinkled ash over the top and sides of the logs. Not thick coverage, just a dusting, perhaps a 1/4-inch layer. The ash served multiple purposes. It reduced radiant heat loss from the logs, slowed the initial ignition, and created a slightly oxygen-limited environment that favored slow combustion over rapid burning. He adjusted the position of bark sheets that covered the smoke holes in the roof, directly above our fire pit. The smoke holes could be partially closed to reduce draft, slowing the fire's burn rate. He left perhaps 60% of the opening uncovered, enough for smoke and hot air to escape, not so much that the draft would pull heat away rapidly. This adjustment was seasonal. In colder weather, he'd close the holes more. in warmer weather less. Finally, he swept the area around the pit, removing any stray ash or coals that might be a fire hazard, and settled onto his sleeping platform. The fire preparation had taken perhaps 15 minutes. Careful work, but not complicated once you understood the principles. I lay awake for the first hour, watching the fire transition from evening to night mode. The logs didn't flame. They glowed, gasified slowly, produced coals that settled into the pit. The heat output was substantial initially, but gradually moderated as the ash coating dried and the logs established their slow burn pattern. By the second hour, I could see only faint glowing through the ash cover, but I could feel steady warmth radiating from the pit. I woke once in the night, perhaps 4 hours after the fire was set. The Longhouse was comfortably warm, not hot, but warm enough that I was comfortable under moderate covering. I checked the fire, still glowing beneath its ash cover, still burning, still generating heat. The logs had burned perhaps halfway through, converting slowly from wood to coals, releasing their energy at exactly the rate needed to maintain comfort. Morning came without waking for fire tending. The 3 large logs had converted to coals overnight, forming a deep bed that required only fresh kindling to rebuild flames. Tekari Hoken uncovered the coals, added small wood, and within minutes had a strong fire burning. The night protocol had worked perfectly, 8 hours of heat with no intervention, minimal fuel consumption, complete safety. I understood then that the night fire protocol was as important as the pit design itself. The hardware, the pit, the stones, the earth, provided the infrastructure for thermal storage and distribution. But the software, the protocols for wood selection, stacking, ash coverage, smoke hole adjustment, determined how effectively that infrastructure performed. Both were necessary. Neither alone was sufficient. The 8th day, I decided to quantify what I'd been observing. How much wood did the inverted fire actually consume compared to conventional fires? I'd been burning wood all week, but I hadn't carefully measured input. Now I wanted numbers, objective comparisons that would demonstrate whether the inverted fire was truly more efficient or just felt more efficient. I started by estimating my wood consumption from the first night. When I'd used conventional fire building methods, I'd added wood roughly every 2 hours through the night, perhaps 6 interventions. Each addition was maybe 3 pieces of split wood, each piece perhaps 4 inches in diameter and 18 inches long. Total, 18 pieces, approximately 2 cubic feet of split wood. In terms of weight, maybe 60 pounds of oak. For comparison, I measured the wood consumed by the inverted fire over a full day-night cycle. Morning fire, medium-sized wood to rebuild from coals, perhaps 6 pieces, total half cubic foot, 20 pounds. Afternoon fire, no addition, just letting the morning fire burn down. Evening fire, 3 large logs for overnight, approximately 1.5 cubic feet, 45 pounds. Total, 2 cubic feet, 65 pounds. Wait, those numbers were nearly identical. How could the inverted fire be more efficient if it consumed the same weight of wood? I reconsiderated my analysis. The conventional fire had heated the Longhouse poorly, maintaining only marginal comfort. The inverted fire maintained substantially better comfort. So the efficiency wasn't in absolute fuel consumption, it was in heat delivered per unit of fuel burned. I refined my calculation. The conventional fire generated heat, but much of that heat escaped directly through the smoke holes without warming the living space. I estimated perhaps 30% of the heat actually contributed to space heating. The rest went up and out. The inverted fire, by contrast, heated the thermal mass first, which then released heat, slowly. I estimated perhaps 70% of the heat contributed to space heating, only 30% was lost. If these estimates were correct, then for equivalent heat delivery, the inverted fire would require roughly 30/70 equals 43% of the fuel a conventional fire would need. Put differently, the inverted fire was about 2.3 times more efficient at converting wood to usable heat. This matched my subjective experience. The Longhouse was noticeably warmer with the inverted fire than it had been with my conventional fires, despite similar fuel inputs. But there was another efficiency factor: combustion completeness. My conventional fires had produced substantial ash and incompletely burned wood, chunks that charred on the outside but didn't convert fully to coals. The inverted fire produced much less residue. Most of the wood converted to fine ash, indicating more complete combustion. Incomplete combustion wastes the energy in the wood. Complete combustion extracts it. I collected and weighed ash from both fire types. Conventional fire residue from one night, roughly 8 pounds of ash and chunks. Inverted fire residue from one day-night cycle, roughly 3 pounds of fine ash. The difference was stark. The inverted fire extracted more energy from each pound of wood, leaving less residue behind. The slow, controlled burn of the inverted fire allowed time for complete gasification and combustion of wood volatiles. In a conventional fire, especially one built hurriedly or allowed to burn too hot, volatiles escape without burning, visible as white or gray smoke. The inverted fire's minimal smoke indicated that volatiles were burning, not escaping. Their energy was being captured rather than lost. That afternoon, I calculated the total heating efficiency, including both heat distribution and combustion completeness. If the inverted fire delivered 70% of its heat to the space versus 30% for conventional, and extracted 90% of the wood's energy through complete combustion versus 70% for conventional, the combined efficiency was 0.70 times 0.90 divided by 0.30 times 0.70 equals 0.63 divided by 0.21 equals 3.0. The inverted fire was approximately 3 times more efficient overall. This meant that a family using the inverted fire method could heat their longhouse through winter with 1/3 the wood a family using conventional fires would require. Over a full winter, 5 months of heating, this was the difference between cutting and storing perhaps 3 cords of wood versus 9 cords. The labor savings alone justified the effort of digging and lining the fire pits. By evening, I had numbers that supported what Takari Hoken had demonstrated through practice. The inverted fire wasn't just a different way to build fires. It was a fundamentally more efficient heating system. The efficiency came from multiple factors working together: thermal mass storage, radiant heat distribution, controlled combustion, complete fuel conversion. Remove any one factor, and efficiency would decline. The 9th day brought understanding that had been building throughout the week. The inverted fire pit wasn't just a clever technique for burning wood. It represented a complete reconceptualization of the relationship between fire and earth. Instead of building fires on top of the ground, separating them from the earth, the Haudenosaunee had integrated fire and earth into a single heating system. I'd been thinking of the earth as passive, a foundation, a material to build in or on, something stable and inert. But the inverted fire pit transformed the earth into active infrastructure. The earth became a battery, charged daily by the fire, discharging nightly to maintain warmth. The earth became a heat distributor, conducting warmth laterally through the floor, spreading it throughout the longhouse. The earth became a temperature stabilizer, moderating swings between hot and cold, preventing extremes. This integration required understanding Earth's thermal properties, its heat capacity, thermal conductivity, thermal mass. The builders knew through observation and experimentation that Earth could store significant heat if brought into contact with high temperatures. They knew that stored heat would release slowly, over hours, maintaining warmth after the fire died. They knew that Earth was abundant, renewable, required no harvesting or processing beyond excavation. The pit design maximized earth contact with fire. The stone lining conducted heat to the earth behind it. The stone floor conducted heat to the earth and sand below. The pit's depth ensured that a large volume of earth participated in the thermal system, not just the surface layer, but earth extending 2 feet or more in all directions from the pit. This large volume meant large storage capacity, large thermal inertia, large stabilizing effect. I thought about European heating methods, raised fireplaces, stoves, braziers, all built above ground level, all deliberately separated from the earth. The one separation was considered desirable. It prevented heat loss into the ground, kept the fire elevated where people could gather around it, made the fire more visible and accessible. But that separation came at a cost. All the heat had to stay in the air, which meant maintaining continuous fire to prevent cooling. The Haudenosaunee had chosen the opposite approach. Embrace the earth, work with it, make it part of the solution rather than treating it as a problem. This choice required different thinking. You had to plan ahead, had to charge the thermal battery during the day to benefit from it at night. You couldn't get instant heat from a cold start. You needed time to bring the earth up to temperature. But once charged, the system maintained itself with minimal input. That afternoon I asked Takari Hoken, through gestures and the few words we shared, when they'd developed this fire pit design. He didn't understand the question at first, but eventually he gestured to indicate a long time, many generations. This wasn't recent innovation. This was ancient technology, refined over centuries, passed down as traditional knowledge. I wondered about the development process. The first pits would have been simple depressions, barely recessed into the floor. Someone would have noticed that fires built in depressions retained heat longer than fires built on level ground. That observation would lead to experimentation, deeper pits, lined pits, pits with sand layers. Each generation would refine the design, adding improvements, discovering new principles. Eventually, they'd arrive at the 18-inch deep, stone-lined, carefully dimensioned pits I was studying. The knowledge wasn't written, it was embodied in practice. Young people learned by watching elders build fires, by practicing under supervision, by understanding through experience how the system worked. The knowledge was resilient. It couldn't be lost in a fire that destroyed books, couldn't be forgotten if one generation failed to write it down. As long as people continued building fires in pits, continued observing and adjusting, the knowledge persisted. By evening, I'd come to see the inverted fire pit as more than a survival technique. It was a philosophy made manifest, a way of thinking about human relationship with the environment. Instead of dominating nature, consuming resources as quickly as possible, the Haudenosaunee had found ways to work with natural principles, thermal mass, conductivity, storage, to achieve their goals with minimal resource input. The earth wasn't an obstacle to overcome, it was a partner in creating comfort and safety. The 10th day, my time with the Haudenosaunee family was ending. I'd learned what I came to learn and more, not just how the inverted fire pit worked, but why it worked, what principles it embodied, what it revealed about the builder's understanding of heat and earth and efficiency. I spent the morning organizing my notes, sketching final diagrams, recording observations one last time. The logic of inversion had become clear through the week. Conventional wisdom said, build fires up, stack kindling, build a structure that burns upward, let flames reach high. This approach was intuitive, visible, dramatic, but it was wasteful. The fire consumed fuel rapidly, sent most heat upward and away, required constant attention, provided uneven heating. The inverted approach contradicted conventional wisdom. Build fires down. Stack large fuel at bottom, small at top, burn downward through layers. This approach was counterintuitive. You had to trust that the large logs at the bottom would eventually ignite and burn. But trusting the process yielded dramatic benefits: slow controlled combustion, complete fuel conversion, thermal mass charging, radiant heat distribution, sustained warmth without intervention. The inversion wasn't just physical, it was conceptual. Instead of generating heat continuously to counteract heat loss, the system stored heat to buffer against loss. Instead of fighting the Earth's tendency to absorb heat, the system leveraged that tendency to create storage. Instead of viewing fire as something to be contained above ground, the system integrated fire with earth below ground. I thought about Henri Beaumont's dismissal of indigenous practices, his assumption that European methods were inherently superior. He'd never examined whether his assumptions were correct, never tested whether there might be better approaches. The inverted fire pit proved that better approaches existed, that different cultures had developed solutions Europeans hadn't imagined. That wisdom could be found by observing and learning, rather than assuming and dismissing. The fire pit taught me humility. I'd arrived confident in my fire-building skills, and my first night's conventional fire had been adequate by European standards. It kept me alive, provided some warmth. But adequate isn't optimal. The inverted fire was optimal for this context, this climate, this building type. It achieved better results with less input, sustained comfort with less effort, demonstrated sophistication I hadn't anticipated. That afternoon, Takari Hoken helped me build one final fire using the inverted method. I selected the logs carefully, sized them correctly, spaced them properly. I lit from the top, watched the burn pattern develop, monitored the heat distribution. The fire performed as expected: clean combustion, minimal smoke, steady heat output, stone warming, earth charging. I'd learned the technique, but more importantly, I'd learned the principles. I could adapt these principles to other contexts, other pit designs, other heating challenges. As I prepared to leave, I took final temperature measurements. Outside, 12 degrees Fahrenheit. Inside, near the fire pit, 61 degrees. Inside, far end of Longhouse, 49 degrees. The differential was substantial, 49 to 50 degrees warmer inside than out, maintained by a fire that would burn unattended through the night on 3 logs. I thanked Takari Hoken and his family, though words felt inadequate for what they'd taught me. They'd shared their technology freely, patiently corrected my errors, allowed me to study their home and practices. They demonstrated that sophisticated heating technology didn't require European materials or methods, that indigenous knowledge was deep and valuable, that learning required openness rather than assumptions of superiority. I carried my journals and sketches away from the Longhouse, back toward European settlements, back to a world that mostly dismissed indigenous practices as primitive. I would document what I'd learned, would share the principles with anyone who would listen, though I suspected few would implement them. The inverted fire pit required abandoning conventional assumptions, trusting counterintuitive methods, accepting that indigenous peoples had solved problems Europeans hadn't recognized. The upside-down fire pit stayed warm all night because it inverted not just the fire, but the entire heating strategy. It stored instead of generated, distributed instead of concentrated, integrated instead of separated. It treated Earth as partner rather than obstacle, embraced thermal mass rather than fighting it, optimized for efficiency rather than tradition. That was the lesson worth preserving. Solutions exist outside conventional frameworks. Wisdom resides in unexpected places, and the willingness to observe, question, and learn leads to understanding that assumptions alone never achieve. The Haudenosaunee had mastered winter heating centuries before Europeans arrived, and their solution remained superior in efficiency, sustainability, and elegance. That superiority deserved recognition, study, and respect, not dismissal, not mockery, but genuine engagement with knowledge earned through generations of careful observation and refinement.